Welcome to the Guardian Group podcast series. The Guardian Group, providing extraordinary solutions to today's exceptional problems.
Hello, and wherever you may be, this is Todd Comey again with Guardian Group, along with Rick Murrah here. We're here today to talk about electrical testing of unpopulated PCBs. Thanks for joining us. Today we'll talk about PCBs, testing, equipment, programming, and the like. So welcome, Rick.
Thank you, Todd. It's always a pleasure having a chit chat with you about electrical tests and various activities. I think in today's podcast, what are we going to discussing? Electrical test of unpopulated PCBs.
So what is electrical test for an unassembled PCB? When people talk about in manufacturing about electrical test, a lot of people, it strikes fear in their hearts of what it actually is. Is it a black hole? And what do you deal with when you're dealing with electrical test? So, Rick, why don't you give us a little background of why we even need PCBs today?
Yeah, Todd, you started it off right there. So, electrical test of a bare printed circuit board, but why do we need PCBs? You know what? Not many people know this, but without PCBs, we would have no modern electronics. We'd have no mobile phones. We'd have no 50-inch flat screens or 60-inch flat screens. Imagine this, a TV in 1948. TV in 1948, in order to make it work, they took all the semiconductors, all the components, and they hand soldered the leads of the components together, creating a spider web, a network of mumble jumble that was used to power the circuitry of the TV. I just find that amusing how they were able to do that, but repeatability is never the same.
Yeah, exactly, Rick. One thing I noticed, if you picture the inside of an old 1948 TV with all the wires and all that, I mean, there was a schematic for that, but if you were to look at it compared to today's designs of equipment, you'd have to have another degree just to be able to figure out what wire goes where and what component does what. That was pretty interesting back then compared to today.
So that leads us to what is a PCB? A PCB is just that. It's a connection device. It holds the components and connects the components in a certain circuit that is driven by a schematic or a flow diagram of the electronic device that is being used. So each one of those green traces, most boards have green solder resist on them, or mask as people call it. But in many cases, they can be different colors of mask on a printed circuit board, but they all do the same thing, whether you have a green board, blue board, red board, pink board, purple board. They all electrically move current from one device to another that makes some sort of functionality of that device work.
Exactly. So what you would think of going back to that old TV that you had when you were growing up, for most of you old like me, you had a console that was like 2 feet by 2 feet or better with a giant tube and a whole bunch of wires. Well, the PCB nowadays can allow that size of a machine to be down where you can actually even look at a TV on your new Apple Watch if you really wanted to. So that's what PCBs are all about today. So I'll take this. Oh, go ahead.
No, go ahead, Todd.
If you look at today's PCBs, the flat screens, 50-inch, 70-inch, even the HD or Ultra HD, they all have circuit boards of these PCBs in there, replacing all those wires and things and tubes. And the circuit boards that are inside these might be only 3 by 3 inches, and there might be only 2 or 3 circuit boards in the complex TV nowadays, which most of your TVs today now are so lightweight because of this, and they use LCD or LED, mostly LED screens now, and most of the size of the TV today is all based on the screen. It has very little to do with all the components, and that's also why there's so much lower power requirements for the newer TVs than the old cathode ray tubes and tube units. Let's get into a little bit about what circuits are all about, and when we talk about we're testing for opens and shorts, what we're actually doing. I'll let Rick explain a little bit of the theory behind what is a circuit.
Thank you, Todd. So a circuit is just that. It's something that allows for some sort of electricity that creates current that does something. So you have to have a complete circuit in order for the current to flow. So imagine a simple circuit with a battery, a light bulb, and a switch. So if the battery is connected to the plus side of the battery is connected to the switch, and then from the switch it goes to the light bulb, and then from the light bulb, one side of the light bulb to the other side of the light bulb, we connect to the negative part of the battery. When the switch is open, there's no current flow because there's nowhere for the electrical voltage to move. So the voltage can move from the plus side of the battery to the switch, but it's open. So there's no current flow, so nothing happens. But what happens when you close the switch? The switch then allows for the current to flow. So when the voltage and current are moving around the loop, all of a sudden it comes to the filament of the light bulb, and there's power there. So that current flow creates illumination of the light bulb, and it completes the circuit and runs back to the negative part of the battery. This is the same thing that happens on a PCB. The PCB has green traces. These traces make current flow. They have a resistance. Todd, maybe you could speak a little bit about, I know it's important to know circuitry, but we need to also have some sort of flow to the circuit to know that when we want to turn on the light switch, that the circuit actually is made in a way that the light switch will turn on light 1 or light 2, depending on how the path of current goes. Maybe you could explain and let us know how that works.
So that's getting into what we call the net list or the mapping, as we can call it in the electrical test world. But in your house, you think about you have a big circuit breaker that's in the garage or in the basement or somewhere in the house with a bunch of switches, and all those switches work for different parts of the house, which you might have one switch for the living room area for the plugs, and one switch for the dishwasher, and one switch for the AC unit that you have. Well, these are all individual circuits, or in the world of the PCB, we can call that a net or a network, which means all those wires are connected together to form a network. And in electrical tests or in circuit boards, when they design these things, they output what they call a net list. From the design side, it's the original net list or electrical map of what the PCB is designed to do. So if power is put on test point number 1, and in the same net you have 2 other test points that are endpoints or branches of the original, then you'll have test point 2 and test point 3. So if you were to put a meter on any of those 3 test points, you would have continuity, or they would be connected. Now, in netlist, there's multiple nets, just like I talked about in the scenario of the garage power, that you have multiple nets so that you don't want them talking to one another. So you will have like net 1, net 2, net 3, like I said, for the dishwasher, the living room, and the air conditioner. You don't want those to interfere with each other, because if they do, then we have big problems. So a net list is an isolation between all of the different points. Multiple points are connected to form a circuit or a net. Sometimes they call them nodes. And then a combination of all them, either listed or in a program or some type, is called a net list. So an electrical test, when we were talking about power and voltage and resistance, it all comes down to some very, very old electrical test theories and laws that we just can't get away from. And one of them is called Ohm's law, which my colleague Rick will kind of tell you what that's all about.
So that's right. It's a very old fundamental base of electronics. Even today in school, if you have children or you're very young, you go to school, you still learn Ohm's law. It's a fundamental part of any electronic device. And it's simply stated that the volts equals I times R, which it means the voltage equals current times resistance. And you can rearrange that formula in various ways. For example, if you want to know the resistance of something, you want to put the voltage over the current and make a division. It would tell you the resistance. The reason why I mentioned resistance, and when we talk about electrical tests of a bare printed circuit board, we don't have any ICs on there. We have no resistors. We have no capacitors. We have basic information. So when we're doing electrical test, the real basic form of electrical test, we want to do a resistance-based test. So we're actually measuring the resistance of the copper in the PCB in order to determine something. And I know that Todd mentioned that a netlist is also required. So a netlist uses, in our case, in many electrical testers, it's going to use some sort of XY coordinates. These XY coordinates are used to generate a netlist or to tell the machine exactly where the point is on the PCB. Because everything has to be connected from one point or one node to the next node. If there's something not running between node 1 and node 2, we have a problem. Maybe Todd can explain that a little bit more.
Yeah, Rick, what we're getting at is what if something is not right? And Rick mentioned X, Y, and if you're new to the electrical testing world, X and Y, we talk about that in a grid type format. Just think of X and Y, these coordinates being, wanted to find your house somewhere. You have a XY coordinate based on GPS. You'll have your latitude and longitude. Think of it the same way. The X and Y coordinates, you use those two, and that puts a pinpoint where you're trying to find where this test point might be. So that hopefully that helps a little bit understand that. One of the things when you're having when we do electrical tests, we test for rudimentary. The beginning tests are for basically opens and shorts, whether the one node that has 5 points, they're all connected, and also for shorts to make sure that node 1 is not shorting out to node 2. So when I talk about that, what is an open when we say that? Or sometimes you might hear that as being an open or an infinite or something like that. So an open is basically really what it is. If you were to draw a circle and draw a line to another circle, the two circles are your test points, the line between them being the trace. If it's connected, the line goes from one circle to the next, and that's a good circuit. But if you were to take an eraser and erase part of the line between the two circles, you have just created an open. So what that means is the current can no longer travel from circle A to circle B, and your tester would report an open, and therefore you would have a non-conforming product. I'll let Rick talk about the other side of the coin, which is what if you have too many people involved or a short circuit?
Yeah, Todd. So the construction of a printed circuit board is not so easily done. There's a lot of metallization in there. There's a lot of copper. It's built in multiple layers stacked on top of each other. They can be one layer of copper. They can be two layers of copper. They can be up to X number of layers of copper. I've seen some up to 52 layers of copper before. And this copper starts from copper foil, some sort of prepreg with copper on one side, glass material on another, and then copper on the opposite side, a copper foil on the opposite side. So what this happens, in order to get the traces, you have to do some sort of imaging in a printed circuit board. So there's a lot of chemistry involved, metallization, and sometimes things just don't go right. And that's when Todd used the example of an eraser. There could be dirt, dust. If there's dust on the resist, then all of a sudden you could etch away the part of the trace where you actually wanted. Similarly, if you have two traces running side by side, for example, so you have two circles vertically above each other with a line collecting, crossing them left and right, you now have two traces parallel to each other with some sort of connector on each side. And if there was some sort of additional electric conducting material between the two traces, you're going to have something called a short. Or you don't etch away that particular piece of copper, you're going to have a short. So now if we come back to the current flow, when it gets to that short, it can go two directions. So of course it's going to branch out. It's going to go to the branch that you wanted it to go, plus it's going to go to the branch that you didn't want it to go. So what happens there is now we have a reading on somewhere where we shouldn't have a reading. In electrical tests, we measure resistance. So from point A to point B, we say there should be X number of resistance using Ohm's law. So there's a really complex formula that calculates the resistance of the trace based on the weight of the copper plating, the length of the trace. You have a value, but you also set up your electrical testers with some sort of test parameters that have a threshold. Maybe Todd can talk a little bit about the electrical test thresholds.
Okay, thanks, Rick. Electrical test thresholds. Well, in the electrical test or printed circuit board manufacturing world, we build a lot of products and we build them based on recipes and requirements. And when it comes down to that, there's some really smart people out there that have developed what we call specifications or industry guidelines. And one of them is IPC. Many of you might be familiar with the IPC group. They have a lot to do with building of printed circuits as far as what requirements, what types of boundaries can be used. Well, in electrical tests, there's also the same group, IPC, and just so happens that Rick and I both sit on a board that develops the standard of IPC 9252, which is the one that is specific to electrical test. And with that, we have some guidelines in that as well. So when we talk about testing for opens and shorts and resistive and voltage and isolation, we look at this document and we find out that when we're doing electrical tests, we need to use, for the most part, a minimum of 40 volts. This derives from older, long-time specifications with the United States military for older manual tests. So we needed to use, this has stayed with us for years. So we use a 40 volt test, and that doesn't mean that you have to no matter what. They say a minimum. Now, what this comes down to is whether or not the customer requires that. They a lot of times will give you a specification document, a procurement document, or what we call a fabrication drawing. And a lot of times there's notes in there that said electrical test needs to be done per IPC 9252. And they may give a class number or a test level number. And that all pertains to a nice graphic chart in that specification. But long story short, so then the continuity value, which is the value that we want to, when I had my explanation of the circle and a line and a circle, if you were to put an ohm meter on that from end to end, we're looking at what's called the continuity. So what we look at in the specification is the threshold is what is the maximum can that be before we want our electrical test equipment to call that a fault. Very commonly in most commercial type PCBs, that number is usually 20 ohms. So if we were to put a probe on one circle and a probe on another circle and we read the resistance, if it's anywhere less than 20 ohms, then the machine will report pass. Now, if they're, like I said, I'd put my eraser in there and erased it, then all of a sudden we would have basically zero or infinite, and which is obviously more than 20 ohms. So then it would report a failure. As well as that, we also have what we call isolation, or sometimes called discontinuity, or basically shorts. We have a value where if in Rick's scenario where we have drawn two lines parallel to one another, and we actually have four circles, that when we put a probe on one of the circle with the one line and one of the circle on the other line, we basically don't want to see any interference or crosstalk, or that's what's called isolation. In the specifications of today for a standard build PCB, that value should not exceed, well, there should be an isolation that is greater than or equal to 10 megohms. And when I say 10 megohms, that would be 10 million ohms. So anything of that value or higher would be considered okay, and the machine would report pass. If there was a value less than 10 million ohms, the machine would report a fault. And in today's equipment, they're rather smart, so they can actually tell you whether or not you have a full piece of copper between the two, which is called a dead short, which you would get basically 0 ohms between the two circles, or you might get something that is somewhere between 0 and 10 million ohms, which we call a leak. And this could be caused by a great many things, and there's some really smart algorithms out there that can help you do that or find those without blowing up the PCB. And with that, that's basically the opens and shorts idea of the whole thing. And with that, I will let Rick, when I talked about that leakage or weird type of short, there's some really cool stuff that we can do to find that. And I'll let Rick explain kind of what we mean by micro short or leak.
Todd, we really do use Ohm's law in electrical test of bare printed circuit boards.
Yeah, the thing about that is I know somebody's going to say, and I know I've had many people in my life tell me that, well, you can't do that. And I said, well, yes, you can, because you can't get away from Ohm's law. But then the argument is made, okay, that you're going to go and put 40 volts of voltage across, and I put my meter on there, and it says I only have like 3 ohms of resistance. So if I take 40 and divide by 3, you got so much current you could light up half of Manhattan with that. And I say, yes, but we know what Ohm's law is going to do, but we have to put some safeguards in there. So when we apply our voltage, we use what we call shunt or buffering circuitry, where we only allow a very small amount of the current to be able to run against the node to make sure that we don't have opens or shorts. And we also have detection circuitry that if we do have a runaway scenario, that the actual machine will trip before any very high currents will be hitting the PCB, because we understand that basically when you learn Ohm's law, you're going to try to apply that V equals IR, and just basically 1 volt across 1 ohm equals 1 amp. And there's no circuit board in the world that can handle that. So that's why we have some buffering circuitry in there with Ohm's law. So I'll let Rick there explain some more, since I diverged into that, but we'll go back to talk about leakage.
That's very interesting, Todd. There's a lot of information there. When we talk about electrical tests, we're right now in this podcast only talking about the high level information. But Todd is right. We have other things in our electrical tests. There's something called a micro short, where we have a leakage, where we have even as small as a human hair. A human hair is 70 microns, and a sliver 70 microns laying across the circuit board will cause problems. So we have something called micro short detection test. We have something called high pot, where we're looking for the
High pot's looking for dielectric breakdown there, Rick.
Yeah, I had a memory loss. And then insulation resistance. High pot is looking for dielectric breakdown. We're seeing now inductance testing. So stay tuned. I'm sure we'll cover all these with a deeper dive, Todd, in our future podcasts.
Absolutely. Well, folks, I think this kind of wraps out. We've taken 20 some minutes, I think, maybe a little bit more of your time today. But we really appreciate you stopping by and having a listen. This is going to be available probably at your favorite podcast place, and definitely we'll have it on our website at guardian.com. Do you have any closing comments for him, Rick?
It's always a pleasure having a chit chat with you, Todd, and sharing the information, because learning is important. Learning about electrical tests, quality assurance, and the PCB itself. The PCB is not a commodity. A PCB is really a complicated connection device that holds the components. Without a PCB, there would be no modern electronics. The world is not there yet. So I appreciate the time everybody's taken to listen to our podcast. Thank you very much.
All right, Rick, thank you very much for joining us. And wherever you may be, this wraps it up for another episode of the Guardian Group's podcast series. If you want to have any extra information or would like to drop us a line, you can get a hold of Rick or myself, dropping a line to info@guardian.com. That's info@gardien.com. Or check out the website at www.guardian.com. We wish you all the best. Have a good day.